about the coordination compounds. We talked about the naming of coordination compounds. Does anyone remember anything about naming them? For example, when we write the names, how do we list the ligands in the naming of coordination compounds? Yeah, the metal goes at the end, right? The metal is last. The ligands, if anyone remembers, they're listed in alphabetical order. Alphabetical order, and then they have their associated prefixes, right? They have prefixes for the ligands depending on their coordination number. Right, so if you have a polydentate ligand, you have the, bis, tris, tetrachus, so on for multiple ligands, whereas the monodentate ligands, right, we also talked about the different types of ligands. Monodentate meant what? Yeah, it only donates one lone pair electron to the coordination compound, right? Polydentate means you donate two lone pair electrons, right? So if we have something like ethylene, diamine, something that looks like this, H, 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 H. This is a big enough molecule that both of these lone pairs can interact with the coordination compound. So that'd be bidentate. You can have bigger ones where we had the tetraacetate, and then something like carbon monoxide. Right, this was something like this. This was a monodentate ligand, right? It's a relatively small molecule, so only one of these lone pairs will interact at a time with the carbon metal center. Right, so we name them. They just get listed in alphabetical order, and then they have the associated prefixes, right? Like I'm not going to expect you to remember the name of all the ligands. It's a way too short amount of time. So I'll give you a table of the names of the ligands. Probably some of the prefixes, and then for some of the metals, those are relatively straightforward. Just some of them are weird, and you have to use their Latin name for some reason. So like iron, for iron 2, for example, you use ferrate. Other ways you use the same ionic naming convention that you know. Right, so we named them, and we talked a little bit about the trends and the transition elements, right? And most of the anomalies in the trends of the transition elements were due to one thing. Does anyone remember what happens in the transition elements once we get to like period 6? What orbitals do we have to start filling up once we get to period 6? The F orbitals, right? So once we hit period 6, we have to start filling up the F orbitals, which basically means that we're adding a bunch of protons for the same given electron shell. Remember we talked about the onion? So there's basically 14 protons being added whenever we fill up a row or one F sublevel. And so that's what we call the lanthanides. The F block are the lanthanides. And most of the periodic trends that were anomalous, right, where we get a sudden shift in the size, so period 6 and 7, or period 5 and period 6 are roughly the same size because the lanthanide contraction. Right, the lanthanide contraction also affects other things like electronegativity and ionization energy as well. Right, so when we talked about the trends, periodic trends, the lanthanide contraction right, that was kind of the main thing that we discussed, right? Where we have all these extra protons, a lot more nuclear charge for a given electron shell, right? So it contracts those atoms. So lanthanum and actinium are relatively the same size. Yttrium and lanthanum are the same size. Where usually, every time we go down a period on the periodic table, you add another electron shell that expands the size of the atom a little bit, because atoms are like onions with their electrons. And so that's why the size increases. And then basically all the other trends, the periodic trends like electronegativity, ionization energy, those things follow from that same effect as well. There's also, interesting trends as we go from left to right across a group sometimes with the d electrons, and those can usually be attributed to energy favorability or minimization of energy, where you can have, it's more stable to have a half-filled subshell where you take one electron from the s orbital compared to having a full s orbital and 9 electrons in your d orbital. So for example, silver is an atom that does that. Its electron configuration for its valence electrons would be 4s1, 3d10. It's good to have a half-filled s orbital instead of and a full d orbital, rather than having 9 electrons in your d orbital and 2 in your valence s orbital. We're not super focused on those because those are kind of hard to predict just by looking at the periodic table. But the lanthanide contraction is the one that we were kind of concerned with. And then after that, we started talking about our we first talked about isomerization, and isomerization is a big one because you'll be looking a lot at that. Coordination, isomers, coordination, I should put compound isomers, because there is such thing as a coordination isomer, right? These were compounds that have the same chemical formula, but they either have different 3D spatial arrangement. Those would be the stereo isomers, stereo or geometric isomers, or they have different connectivity, and those would be the structural isomers, right? That's how we distinguish those two. So they go from structural. I'm just going to go to the slide just so we remember, right? We have the stereo, different spatial orientation, geometric isomers, optical isomers. You're going to be looking at a lot in organic chemistry when you talk about chirality. That's because these interact with light differently. And coordination compounds, we can either have the geometric isomers or the coordination isomer. The coordination isomer was when we had something like carbon monoxide, right? You have 2 lone pairs there, and each lone pair can coordinate to the metal compound. And which lone pair coordinates gives us a different coordination isomer, right? So the example we used here was the cyanide ion, right? And you can have the lone pair from the carbon coordinating to the iron, or you can have the lone pair from the nitrogen coordinating to the iron, right? So the orientation of this compound is different than the orientation in this compound. And that's like forming a bond, like a different type of bond with another atom, right? So the connectivity of this coordination compound is slightly different. Whereas the geometric isomers, right, these have the same connectivity, but the different 3D spatial arrangement. So what does that mean? Well, if we looked at these 2 organic molecules right here, this is ethylene diamine, right? Here we have both of the amines, the NH3, those are called amine groups, on the carbon atom in both of these compounds. But the spatial orientation is different, right? Here, they're on opposite sides of the double bond, and here they're on the same side of the double bond. So that's what we call a geometric isomer. It's a stereoisomer because even the connectivity is the same, right? This carbon is still bonded to 1 hydrogen, 1 nitrogen, and 1 carbon. This carbon is still bonded to 1 nitrogen, 1 hydrogen, and 1 carbon, right? But the orientation, how they look in 3-dimensional space, is different. And again, this is very important for properties, either chemical properties or physical properties of the material. And this, for example, was a cis versus a trans isomer. In the coordination compounds, the shapes aren't, trigonal planar like this, so they're a little bit more complicated. So we talked about cis and trans for square planar structure. We have cis and trans structure, and for octahedral with 2 pairs of 3 unique ligands, you can have the Beck and the Mur isomers, right? And that is if we have one face of the octahedron containing all the same ligands, and here is like the meridian lines that are on the octahedron that contain the same atoms, right? So they look differently in 3-dimensional space, but they have the same connectivity. Both these irons in these cases are each bonded to 3 chlorines. Both the irons are bonded to 3 fluorines, right? But the spatial arrangement, the 3D spatial arrangement, is different from each other. And so only ones we're going to be looking at would be the Beck and the Mur isomers and the cis and trans for square planar structures. You can also have cis and trans for octahedral structures as well. Does anyone remember how you would get a cis or trans octahedral structure? It had to do with the type of ligand that you had. I think I have it on the next. Basically what it was is if you had a polydentate ligand, like ethylene diamine, like we have here, right? The ethylene diamine can either be on the same side of the octahedron for a cis conformation, or they can be on opposite sides. So it's almost like you kind of project this into 2D, like a square planar structure, right? Because you take away those, I guess you can't really see it here. You take away both of those nitrogens there, and that looks like a trans square planar structure. But that's because this ethylene diamine is coordinating to 2 spots on the octahedron. Here you do the same thing. You take away both of the z-axis nitrogen coordinations there, and that looks like a cis square planar. Right? So this is, a little harder to visualize than I'd say traditional, even organic chemistry isomers, but we're just kind of introducing the idea to it. For the purpose of the exam, I'd probably give you something very similar to these ones, right, where it'd be pretty easy to distinguish between them. Right, and so isomerization is really important in chemistry, and a lot of synthesis methods are developed to actually control where you're putting these atoms. And it's kind of interesting to think about that, we don't have any tools, little tiny tools that allow us to place different atoms, but different reaction mechanisms, and you'll learn a lot about that next semester, will control the stereochemistry. And the stereochemistry means where exactly on this atom am I placing what I'm trying to place here. All right, any questions on isomerization? The main idea is to be familiar with structural versus stereoisomers, and the 2 important ones for inorganic chemistry are the geometric and the coordination isomers. Okay, all right, and then we started talking about crystal field theory, where we were discussing hybridization, right? We usually think of hybridization in terms of an s and a p orbital. Those will come together to make 2 sp hybrid orbitals, right? And that's what gives rise to our molecular shape of linear molecules, right? If we take 1 s and 2 p orbitals and hybridize them together, that gives us 3 sp orbitals. Right now, those, based off of Vesper theory, give us our trigonal planar shape. Once we get to more complicated molecules, like our coordination compounds, we get something where we're now start hybridizing the d orbitals with the s and the p orbitals. And so if we hybridize 2 d orbitals, 3 p orbitals, and 1 s orbital, that's like we're saying s plus p plus p plus p plus d plus d. That gives our hybrid sp3 d2 orbitals, which explains something like an octahedral shape. All right, so hybridization is a qualitative way, and it's qualitative, but it is at least somewhat backed up by calculations, right? So this is something people developed before doing the calculations, but it's somewhat backed up by the ideas of quantum mechanics and stuff. But it was developed to describe the shape of these molecules. And so with this hybridization, we get our shapes for our coordination compounds, right? And if you go on to quantum mechanics, you'll learn that the basis for this is that this is an addition of 3 different independent solutions for the atom, and we're saying, well, any sum of them is also a solution for the atom, right? And that's why these hybrid orbitals exist. And so, each sp, this is called an sp orbital, meaning that each one of these is an sp orbital, where we took 2 of these added together to make 2 of those hybrid orbitals. S and p, the sp orbitals, are very important for organic chemistry, because carbon can have sp3, sp2, and sp hybridization. So the shape of proteins, the shape of polymers are all determined by the hybridization of the carbons that exist in the backbone of those polymers. And then we finally got to the the crystal field splitting energy, right? And so we have this picture here to kind of hopefully visualize this a little bit better, right? Normally, all of our d orbitals all exist at the same energy level. But as soon as we add either crystal lattice or ligands to bind to this compound, right, they deform the d orbitals and it causes a splitting in the energy. So if we have this as an example of an octahedral compound, right, octahedral compounds, when they split, the two orbitals that lie along the axis of bonding, right, so what I mean by that is this is each of these black dots represents a ligand, right? These orbitals, the dz squared and dx squared minus y squared, these are the orbitals that lie along the axis of bonding. You're trying to overlap electron density when you put electrons there, right? Because there's already a ligand there that has some electron density. So to put an extra electron in that orbital requires a little bit more energy, right? I already have like a carbon or a cyanide binding group right here, right? This already has a negative charge and it has some electron density associated. So if I try to put an electron, right, in this orbital that's already in line with the ligand there or overlapping with the ligand, it's going to require a little bit more energy to do so, right? I'm trying to overlap this electron where there's already some electron density. So that's why these two orbitals that lie along the bonding axes go up in energy. The three orbitals, so dxy, dxz, dyz, right? These are orbitals that lie in between the axes, right? So see, these orbitals lie exactly on the axis. Here, this orbital lies in between the axis, right? So you're not trying to overlap electron density. You're actually putting it in between places where there's already electron density. So you're filling in the gaps. So those are actually lower in energy, right? Those are going to be lower in energy than your original d orbitals and lower in energy than the ones that lie along the bonding axis. And how these different orbitals deform depends on the type of ligand that you have. So we have strong versus weak field complexes, and all that means is that you have ligands that deform the field strongly or deform the field weakly. And what that interprets is that means that just the energy difference between the splitting is either large or small. Right, so this energy difference depends on the size of the splitting. Right, so this here depends on the ligand, right, or what type of ligands you have. And I'm not going to ask you this type of thing if I give you a mixture of strong and weak field ligands. This would really only be for given all weak field or all strong field ligands. Right, any questions on that? Does it kind of make sense why it's easier to put in electrons between the spaces where the ligands are instead of directly on top of them, right? This space is already taken up by a ligand there. So to put an electron in that orbital just requires more energy. Okay. So that's kind of where we ended off last time. So from this simple description of the d electrons, you can usually determine what the crystal field splitting energy is of these compounds or crystals just based off of the color of the solution, right? So if you have a compound and you're given the color of the solution, what that means is that that compound is absorbing almost all other wavelengths of light except the one you're seeing, right? That one is being either emitted, transmitted through the material, or reflected back at you, right? And what it means is that the compound itself is absorbing what it would be the complementary visible light color to what you're seeing. So if you have a compound that's blue, that means that the compound is actually absorbing in the orange region. And for a compound to absorb in a region like that, that means that the energy, basically the energy difference between the highest occupied molecular orbital, if you guys remember what that is, and the lowest unoccupied molecular orbital, which in this case are deformed d orbitals, is equal to that energy, right? That's what we learned in first semester chemistry when we absorb light at a specific wavelength. Quantum mechanics says we can only absorb, right? That's what quantum mechanics means. We can only absorb certain quanta of light, very specific energy values. And so if something is blue, that means we're absorbing in the orange range. And that means that that energy is associated with that wavelength of light, that energy difference between the d orbitals in this case. And so that energy is called the crystal field splitting energy. Right, so this is the crystal field splitting energy. And if this compound has 6 coordinate or ligands bound to it, what shape would this compound be?
Octahedral.
It should be octahedral, right? So if we were to look at something like this, we could even draw, right? This would be the original d orbitals. After it gets split, right, it binds the ligands, the octahedral compound deforms in the way that we just showed, right? Where we have the 3 off-axis orbitals below and the 2 on-axis orbitals above. NH3 is a charged or anionic or a neutral ligand. Is NH3 charged or neutral?
Oh, wait,
NH3 is neutral, right? NH4 would be the charged, right? The charged ligand. But usually our ligands, they have to be electron donors, right? Lone pair donors. So NH4 wouldn't even work with a coordination compound for that reason. So this is a neutral ligand, which means that the charge on copper is what?
+2.
So the charge on copper is going to be +2, which means that there are how many electrons in the d orbital for copper 2? Right. If we look at the period, we'd have to look at the periodic table, right? So copper is element 29. If we pull out 2 electrons, remember this is where the kind of weird stuff starts to happen. We always pull out the s electrons first. How many s electrons are there? So in that case, it'd be 4 s electrons. There's 2, right? So that means that we would have how many electrons left in the d orbital for copper?
I want to say 7.
So the way we can do this is we know the transition block, that's called the d block elements, right? Every time you add a proton, you add an electron, right? We know we took the electrons from the s orbital, so we don't have to subtract any from the d orbital because there's only 2 electrons missing. Because how do we know that? It's a +2 copper because ammonia is neutral. So to get a total +2 charge, that means the copper itself has to be +2. So we count starting from scandium, number 21, and we count over until we reach copper. Yeah, it'd be 9. So you count over until you reach copper. That tells you how many electrons are in the d orbital for that compound. If it was neutral, then we would still have that many d electrons. It's charged, but we have to take the s electrons first. So it'd be scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper. Okay, I counted wrong the first time, right? So that means there's 9 electrons in the d orbital. So if I was to fill up the d orbital before counting in the splitting here, what would how would I fill that in first?
The first 4. Oh wait, no, you do 1 on each.
Yeah, you do 1 on each, right? That's Hund's rule. First we put in unpaired electrons and then we start to pair them, right? So 1, 2, 3, 4, 5, and then I'm gonna put 4 more in, right? So 1, 2, 3, 4, right? So I have 1 unpaired electron in this case. So now I know how the electrons fill the d orbital when it's not perturbed. When it's perturbed, I still have a crystal, I have a splitting of energy now, and I fill according to the type of ligand that we have. So we either have strong field ligands, strong field means large energy difference, or weak field ligands, that means small energy difference. And how we fill them in depends on that. What we're actually looking for in this problem is the size of this energy gap, right? This energy splitting is what tells us if it's a strong field or a weak field ligand. And what that means is that when I fill in the electrons, remember I filled in each empty one before filling in the next one? If this energy gap is really, really large, then I'm gonna fill in each electron in an empty orbital here. But if this energy gap is really large, it's gonna be lower in energy to pair them before I start filling in the higher energy electrons. If it's a small energy gap, then it'll still probably be energetically favorable to fill in the higher energy electrons, empty first, and then start pairing everything. Right, so depending on the crystal field, splitting energy, or if it's a strong or a weak field ligand, that determines how you're gonna fill in the orbitals. So if we look at ammonia, we see that ammonia is a strong field ligand, right? It's a strong field ligand. The split is usually around, I believe right here, let me double check. Yeah, the split is water, between water and thiocyanate, right? So this is the split between strong and weak field ligands. So since it's a strong field ligand, and this is the magnetic properties we'll talk about in a second, but this is a strong field ligand, NH3 equals strong field, which means delta is large. And how we actually put that into practice now is we know we have 9 electrons to fill up in these 2 split energy levels now. That means that when we start putting in the unpaired electrons, right, 100 joules, these are all equal in energy, so we still fill each empty orbital first. Since this energy gap is large, it's lower, it's easier to start pairing the electrons before we fill in the higher energy levels. So I'm going to start pairing these, so 1, 2, 2, 3, so I have 6 there now, and then I go and fill the remaining 3 in the upper energy level. So in the crystal field, we have the same number of unpaired electrons as the non-perturbed or the unchanged copper atom here. In this case, because it's 9, I think you'll always end up with only 1 unpaired electron. But we filled in these bottom ones first, because delta is large. And we know delta is large because ammonia is a strong field complex. Right? We're just saying it's a lot of energy between these two. And this isn't really what the question is asking, and we don't have to do this part, but I'm just emphasizing this is how we fill in the electrons for these split energy levels now. And that's important, as you saw on the next slide, because this is going to determine magnetic properties. Depending on how, for example, if we had 8 electrons, right? If we fill in the bottom or the top first, you'll end up with more unpaired electrons. More unpaired electrons usually means a larger magnetic moment for the atom, though that becomes a magnetic compound. But what if we want to actually find the energy of the splitting here? What if we're like, okay, I don't know, but I do know what the color of the compound is. Does anyone have any idea how we could find the energy of that gap based off the color of where we're absorbing?
So like how you said, if we're absorbing orange,
Mm-hmm.
it would have to be between the 580 and the 620.
Yeah. Mm-hmm. Yeah, somewhere in that range. How would we calculate that energy? What we can think about is, well, if it's reflecting light, it's usually absorbing and emitting light at that wavelength. And we know that that's going to be associated with this energy difference right here. If it's related to light, right, if this is emitting light at this energy, that means that the energy is associated with the energy of a photon, right? So what is the energy of a photon?
Yeah, is it in coulombs? I remember being like.
Huh?
Is it in coulombs?
It's not going to be in coulombs. If we were looking at energy of electrical things, it's usually volts as a joule per coulomb. But joules are how we always get energy. Usually anything will be in units of joules for SI units. Okay. But does anyone remember what the actual relationship was for the energy of a photon? The energy of a photon is h, which is Planck's constant, fundamental constant of the universe, times the frequency of the light, right? And light is the cosmic speed limit. So light can have different wavelengths and different frequencies. And frequency is in units of what? Does anyone remember? Yeah, hertz, which is inverse seconds, right? So the way the speed of light is conserved for different energy light is because the speed of light is equal to the wavelength times the frequency. The wavelength is in units of length, or meters, nanometers, whatever, and the frequency is inverse seconds. So when you multiply those two together, you get units of meters per second, which is speed, right? And that's where the speed of light comes from. That's our speed limit. So if we know that the energy of what's being reflected by the coordination compound is related to the frequency, we know what wavelength range that exists in, right? We can then determine what is the size of this energy band gap. Because we know the photon energy that it releases is directly related to the energy gap here, right? The energy difference is related to the photon that's released, right? It's conservation of energy. When we go from an excited state to a lower energy state, that energy has to go somewhere that's released in the form of a photon. So the energy of going from an excited state to a lower energy state is exactly equal to the energy released by the photon. It's a way for the system to kind of relax itself, right? There's other ways that systems can relax themselves too, right? If you're vibrating really fast and you're bumping into your neighbors, you're releasing kinetic energy in the collisions and whatnot. Or in this case, it's electronic energy that we're relaxing. The electronic energy of the electron relaxes and releases a photon of that form. So if we know the wavelength, right, we can use the speed of light and our relationship here to rearrange this so that the frequency is equal to the speed of light divided by the wavelength. Plug that back into our expression for the energy of a photon. So this is equal to hc over lambda. This speed of light is fundamental constant. This is a fundamental constant of the universe, right? The only thing that changes between these problems is the wavelength. Where do we get the wavelength from? From the color wheel, right? Which is related to the color of the compound itself. Right, so based off of that, you can get an idea of what this energy gap is. And so if we're around 600, we'll just put it at 600 nanometers. Not everyone's gonna get the same answer for these problems because it depends on what exact wavelength you choose. This is gonna be equal to 6.626 times 10 to the minus 34 joule seconds. That's h times the speed of light, which is 2.998 times 10 to the 8 meters per second, divided by, and we're gonna have 600 times 10 to the minus 9 meters. I can't just put nanometers because I need the units of meters to cancel out for this problem. Right, if I look at this, I see meters cancels out with meters, seconds cancels out with seconds, and I'm left with this energy of joules. All right, so if I were to plug all this into a calculator, what would I get? I would get something like 10 to the minus 17 joules. So this would give me, when I did the notes for this, I didn't put it in a calculator either. 6.626 times 10, or times 3, divided by 600 times 10 to the minus 17, just combining all that, that's in joules. If I wanted it in units per mole, how would I convert this to units per mole? This is a very, very small energy value, right? This is gonna be like 10 to the minus 19. So this would be the energy of a photon released from a single ion, right? A single complex ion. So this we can think of as the energy per ion, right? Or per complex ion. How would I convert that to per mole of complex ion? Right, this is per complex ion. How many complex ions are in a mole? A mole of complex ions. How many complex ions are in a mole of complex ions? What is a mole? Yeah, you always use Avogadro. Whenever we're going from moles, so whenever you see energies, I guarantee you go farther in chemistry, thermodynamics, you see, when you see per mole, you're like, what is, like, how do I think about that? All they're doing is just introducing Avogadro's number to a calculation like this. Right, because this is saying this is the energy per complex ion. How many complex ions are in a mole? Even if you don't know the exact number, the name of the number. There's an Avogadro number of complex ions in a mole of complex ions, right? So there's 6.022 times 10 to the 23 complex ions per mole of complex ions. So now we're going to get an energy value, right? If we have a mole of these complex ions in solution, that's much more reasonable from what we're looking at. We're not going to have something like 10 to the minus 17. We're going to have something like 10 to the 5 or something along those lines, or 10 to the 3, like a kilojoule per mole. All right, so now this will give us the units of energy per mole. So if I were to plug all of that in, I didn't do it when I did the notes. So I got to plug it in myself. All right, so it would be 6.022 times 6.626 times 3 divided by 600. That's 0.19, 0.19. Okay, 0.20 is too many nines. 0.20 times 10 to the minus 17 times 10 to the, that'll be times 10 to the 6. So this will be like 2.0 times 10 to the 5 kilojoules, or joules per mole. Joules per mole. I'm running out of space here. It'll be 2.0 times 10 to the 5 joules per mole of complex ions, which is, what is it, 200 kilojoules per mole. And so it might be hard to grasp this idea the first time we look at it, because it's a relatively complicated process that we're doing a lot of assumptions just by looking at the color of a compound. And it's not that far off of what this energy splitting actually would be. But the only thing that changes when you're looking at this problem from one compound to another, if it's a colored compound, is just where you're absorbing and where you're reflecting light. Right? So this compound was blue, so we're in the orange region. If it was a blue-purple, we'd be absorbing or emitting in the reflecting in the yellow region. So the only thing that changes in any of these problems is just the wavelength that you're looking at. I mean, that's the only thing that changes in these problems. Okay, any questions on that? So this is most likely, most definitely will show up on the final. This will be related to the free response question for the crystal field theory. Aaron?
So you said that we would get a different number based on what we choose.
Yeah.
Would you give us something specific, or would we just?
I'll give you the color wheel, so you don't have to memorize what colors or what wavelength. But for example, you might have a slightly different number than what I did because you said, well, it's blue, I didn't choose 600, I chose 615 or something like that. That's still within the range of orange. As long as your wavelength is within, you know, that range of 620 to 580, that's fine, that's understandable. But I mean, really, the only part of this calculation that changes is this number for the wavelength. Right, we're only looking at colored compounds. Transition metals tend to just absorb this splitting, crystal field splitting energy just tends to be in the visible range for all compounds. And the exact reason for the color wheel making sense here, that's, you know, more of a discussion for time reversal symmetry in Einstein, why the complementary color is what we emit there. All right, any other questions, please? So like I said, this will definitely show up. It'll be part of the free response question at least, if not the entire free response. Okay. And so I talked a little bit about how we fill up the d orbitals once they've been deformed by the crystal field. And the reason that's important is because it's important for the magnetic properties of these metal centers. So we can either have low spin complexes, which these are just going to be complexes with a low number of unpaired electrons. And these are going to be from usually strong field ligands. Let me write that a little bit. So the strong field ligands are usually going to be low spin complexes because we always start pairing the electrons before we jump up the energy gap. So for example, if we have 5d electrons and we want to put it into so this is strong field, that means that we first fill in the lower energy level. It's a strong field, which means that we fill in the entire bottom row here, the bottom energy level, before we move up in energy. So we put the remaining 2 in the off-axis d orbitals. If we now were to put that in a weak field, right? Now what we're saying is that the ligands, right, this energy difference is really small. It's smaller than the pairing electron, or the pairing energy of different electrons. So first, we put in our 3 unpaired electrons, and now it's lower in energy to start filling in the higher energy levels than it is to start pairing them. So we just use our normal Hund's rule there. We're filling in all the empty orbitals first. So then we put these up here. So if we look at this now, we say, well, for a low spin complex, these are usually strong field ligands because when we had 5 electrons, we only have 1 unpaired electron right here, right? Whereas in a weak field, the same 5 electrons now have 5 unpaired electrons here, right? So the magnetic properties for these two materials are going to be very different from each other. The more unpaired electrons, the stronger response we have to magnetic field, or even generating its own magnetic field. So high spin complex are going to be complexes with a high number of unpaired electrons. And these are usually going to be weak field ligands. And whether it's strong or weak field, right? All that depends on is the specific ligand. So I'll give you guys this chart. I'll give you a compound, and I say what is the electron configuration for the d orbitals for this metal complex, right? And all that means, or what is the orbital diagram, is draw out the orbital diagram for the d electrons for this complex based off of what ligand you see in this chart. You can then determine how do I fill up the electrons for this atom. If you have 9 electrons, for example, though, then no matter whether it's strong field or weak field, you'll always have a low spin complex. That's why it depends on the metal as well. If you have 9 d electrons, you're always only going to have one unpaired electron, whether you're strong field or weak field. Why? Because you only have one spot left to fill no matter what. Right, so a way you kind of add on to these, you say, well, is it a high spin complex or a low spin complex? What does that entail? It just entails an understanding if it's a strong or weak field ligand. Okay, so let's see, how would we do that? Let's do one example. Let's do the cobalt, or if we were to name this compound, how would we name this? What would the prefix be for the fluorine there, right? Ligands go first?
Hexafluoro?
Yep, it would be hexa, fluoro, cobalt. Right, so that one's not too bad. This one, on the other side, might be a little bit more annoying to tell you, right? We have amine, 5 amines, pentaamine, and then the nitrite, which becomes nitrito. Right, so what's the charge on this cobalt here? Right, what's the charge on each fluorine, associated with each fluorine atom? -1, so total we have -6 for each of them, right? And the total charge on the complex ion is what? -3, right? So what does the charge on cobalt have to be to get -3 for total? +3, right? So this has to be 3+. So this is cobalt 3+. What is the electron configuration for cobalt 3+, right? We're taking away how many electrons from cobalt? 3, right? So let's say neutral cobalt. Let's do electron configuration, neutral. If we were to do the abbreviated electron configuration, that would be cobalt most recently as argon, right? After argon, we fill in which s orbital?
No. Or wait.
Before we do, we're going to do the neutral, and then we'll go to the ion. Yeah. So it's 4s2, right? And then how many electrons to get to neutral cobalt? Remember, we can count across the d block until we get there. So scandium, titanium, yeah, it should be 7, right? So cobalt, so it'll be 3d7. This is for neutral cobalt. To go to cobalt 3+, we take away 3 electrons, right? Where do 2 of those electrons come from that we take away? From the s orbital, right? We always take away from the s orbital before we take away from the d orbital. So what should the abbreviated electron configuration be for cobalt 3+? Yep, we'll have 4 as 0, right? You don't have to put the 4 as 0. I'm just doing that to illustrate that we've taken 2 electrons away. So there's 1 electron we're taking away from the d orbital, so it should be then 3d what? 3d6. All right, why do we need to know this? Because we need to know when we have our original d orbitals, right? We need to know how many we fill in for our octahedral crystal field, right? We need to know how many electrons. So we're going to fill in 6 electrons here. And fluorine, if we go back, let's say, okay, now I know how many d electrons I have. I need to figure out how do I fill this in, right? That depends on the type of ligand, right? Depends on if it's a strong field or a weak field complex. And so we say, okay, well, I don't memorize those because why would I memorize that? We go back here and we see, okay, fluorine is a weak field ligand, right? Which means that, how do we fill this in if it's a weak field ligand? Yeah, we fill all the spaces before we start pairing electrons. Strong field, we fill the lower energy completely before we start filling in the higher energy. Right, so we fill in all the spaces, 1, 2, 3, 4, 5, and then 6. So we see that if it was a strong field complex, we would have no unpaired electrons, right? Because those 2 electrons would be down here. So the fact that it's weak field means that we have 5 unpaired electrons. So this has 4 unpaired electrons. Does that make sense? All right, we look, is strong field or weak field? The other thing we have to determine is, well, we have 6 ligands here, so that tells us that it's an octahedron. What if it was 4 ligands, right? Then what do we do, right? So we haven't really talked about how these d orbitals deform yet when it's not 6 ligands. We'll talk about that next. Okay, any questions? So if we have or a tetrahedral complex, right? So this is no longer a octahedral. These are always going to be higher in energy than your unpaired isolated atom. And the tetrahedron, right, if we have 4 binding partners and we look at where these orbitals lie along our, comparatively to our axis, right, we still have our metal center, but tetrahedrons kind of go in between the spaces, right, so they'll be in each quadrant. This will be kind of hard to draw, but in the back, right, so our ligands exist where I'm drawing the circles now. So unlike the octahedron, where everything lied along the x, y, and z axis, tetrahedrons have stuff that lies in between the axis. And we could think of that because they're not all 90 degrees. The ligands aren't 90 degrees from each other like an octahedron. They're 109, right? They're slightly larger than 90 degrees. So they can't lie exactly along the axes. So what that means now is that the ones that lie along the axis are in between the ligands, and the ones that lie in between the axis are in line with the ligands, right? The xy, xz, and yz d orbitals are overlapping with the ligands now, so it takes extra energy to put an electron in there. The ones that lie along the axis, x squared minus y squared, and the dz squared, those are in between the ligands now, so they're lower in energy. They're generally higher in energy than the unpaired d orbitals, though, no matter what. All right, so what this means is that the d orbitals, I know the resolution's kind of bad, these are always going to deform, where we have 3 on top and 2 on the bottom. Now, that's how once we perturb the system, how they deform like that. All right, so it's just the opposite of an octahedron. And again, the reasoning for that is because the ligands are in the spaces between the axes, which line up with the d orbitals that are in between the axes. The ones on the axis now are the spaces between the ligands. It's easier to put an extra electron in there because you're filling in the space between electron density. All right, so any questions on the tetrahedral structure? Everything else you do for tetrahedrons are the same, right? You still fill in, if it's a strong field tetrahedral structure, then you still fill in the lower energy first before going to higher energy. If it's a weak field tetrahedron, you fill in all of the orbitals before starting to pair them. All right, so it's the exact same idea with that. And then the last one, so the last shape, does anyone remember what the last shape is for these coordination compounds?
Trigonal bipyramidal? Or wait.
Trigonal bipyramidals usually would have a lone pair in there or you'd have I guess you don't necessarily need to have a lone pair. Actually, why don't we see trigonal bipyramidal? It's because the angles aren't exactly equal. They don't really line up with the d orbitals, right? The d orbitals, that's what it is. The d orbitals are responsible for binding. The trigonal doesn't really line up with d orbitals because you always have the orthogonal, x's for the d orbital. The last one is also for binding partners is a square planar complex. So square planar complexes are the weirdest because it splits not just along the axis, but also the interstitial spaces. It splits it into a number of different energies. And so I'm not really going to give you guys any problems where, I might ask you the crystal field splitting energy for a square planar complex, but the actual filling up of these orbitals, we always fill in all of these first before jumping the energy gap. I won't ask you any square planars. But this is how the square planar complex splits in the crystal field, right? So this is the actual splitting energy here. And the reason is because most square planar complexes are always going to be low spin, and they're usually going to be D8 strong field, or D8 metals, and strong field ligands for this. Right, so nickel, palladium, platinum, those are all D8 metals. Those are usually going to be your square planar complexes. Which is why this is represented as the gap, because you fill in 8 electrons before you represent that gap right there, right? 1, 2, 3, 4, 5, 6, 7, 8, and then we go above the gap, which is with strong field, we never fill in these first, right? So it's usually only going to be D8 metals and strong field ligands that form crystal or square planar structures, which is why you see a lot of platinum for square planar. Nickel can be tetrahedral or square planar depending on the ligand, right? So nickel, if it's a weak field ligand, it'll be tetrahedral. If it's strong field, it'll be square planar. So square planar is a little bit more rare, but that's also the interesting metals too. Palladium, platinum, very valuable metals, not just for looks, for platinum, for example, but also important for a lot of catalysis and things like that. And it's the electronic structure that allows these metals to behave as good catalysts. All right, square planar structure allows for different type of docking for reactant molecules to then have their reaction happen. All right, so let's take like a 10-minute break, then we'll start talking about organic chemistry. And organic chemistry will be pretty quick. We'll go over naming and drawing of organic compounds, but this will be what will be covered for the coordination compound, right? And so next time you'll see coordination compounds. Oops.